Okay, we're moving now into 4.4, the contingency table perspective. And we're going to begin by talking about what contingency tables actually are. So, just like Venn diagrams, they're a helpful way of displaying and organizing our work so that we can determine probabilities. Namely, they look like tables, and they work most effectively when we have two categories or two variables or two events that are of interest to us as we're working with the sample space of an experiment. So to motivate that, I have here an example of a longitudinal study that examines a sample of 200 people. In the first part of the study, the 200 people report whether they use menthol e-cigarettes or not. And then those same people are tracked down 2 years later to see if they have developed lung cancer or not. And it doesn't have to be terminal. It can be, any malignancy that is present. So for the ease of calculation, we're going to denote these two events that we're interested in, the use of the e-cigarettes and the developing of cancer, using A, which is used e-cigs, and B being the event in which the randomly select person developed cancer of the lungs. Okay, so notice that this also gives us something about A bar and B bar, namely A bar is no use of e-cigs, and B bar means they did not develop cancer. Maybe it's did not develop it yet. So, in order to organize this, we're going to create a contingency table. And in a contingency table, we have rows and columns. Rows corresponding to A and columns corresponding to B. So namely, my rows are going to be corresponding to A. So I've got A and A bar. And just to remind you, A and A bar means they either used e-cigs or they didn't. So e-cigs or they didn't. And then just for the sake of ease there, let's just use that terminology there. So B, on the other hand, is going to form our columns. So B, remember, is the event in which the randomly selected person develops cancer. So and B, complement, is the event in which they do not develop cancer. I'm going to symbolize it that way. So no cancer. Okay, so what do we want to do with this information? So first of all, we need to know how many people fit into each category, right? So we have some information here that is given to us, namely 45 people used the e-cigs, the rest did not. Of those who used the e-cigs, 19 developed lung cancer. Of those who did not use e-cigs, so non-users, 4 developed lung cancer. So how do we put this all in a table here? What we want to do is we want to make sure we have a spot for all the different possible information. So first of all, so far it looks like this. I'm deliberately putting in an extra row and an extra column because we're actually also going to have our row totals and our column totals. So each cell of this table is going to represent a category in this sample. And the column totals and the row totals are going to tell us something about total number of people in event B, in event A, and so on. So 45 people used e-cigs, which means 45 people are in the category A. So that will go here. And we are not told anything yet, not with this first line, about whether they developed cancer or didn't, so we're not going to assume anything about that. Okay? So right now we're doing the cardinality approach of the contingency table. We can also use probabilities, but we would need to, we would just need to divide by the total number of people in each row. So we know we have 200 people total, so that'll be important. We'll put that there. Now, of those who used the e-cigs, so in this first row A, 19 developed lung cancer. So 19 goes here. Okay? So that's literal information that's been given to us now. And we can infer a little bit in a second, but we'll do that in a second go around. Lastly, we know that of the non-users, 4 developed lung cancer. So that's this category right here. So non-users is A bar and B. So this is the literal information that's been given to us. It's up to us to fill in the rest. How do we do that? Well, process of elimination, some deductive logic here. So if 45 people use e-cigs, that means the remainder didn't. So 200 minus 45, and that should give us 155. So everything I'm writing in blue now is something that we've deduced from the rest of the information. Make sense? Okay, so now we can figure out, because we have B, how many people used e-cigs and didn't develop cancer. So that's 45 minus 19, that's 26. We can also deduce how many people didn't develop cancer and didn't use e-cigs. That's 155 minus 4, 151. And now all we need to do is add down to get the column totals. So we'll figure out the total number of people who developed cancer, and that's 23. And the total number of people who didn't. And if we add down here, so we can do it that way, and get 177. You should check that you did this correctly, in that these two boxes should add up to 200. But it should have worked out. If you didn't do anything, if you got a different answer, then I would start over and see where you might have made a wrong calculation. Okay? So what is so helpful about this is that this tells us actually everything about all the different combinations of events in this sample space. Namely, we now know how many people are in A intersect B, in A bar intersect B, in A intersect B bar, and in A bar intersect B bar. So intersection happens when we're looking at an individual cell, right? Union, on the other hand, is looking at a combination of rows or columns. So putting these two boxes together, the 19 and the 4, gives us 23, which is B. Putting these two boxes together gives us 177, which is the total for B bar. And though similarly, the row totals are telling us the totals for A and A bar. So we have essentially all the information we could possibly want about these two events in the sample space, S. And using that, we can now calculate some interesting probabilities. So for instance, let's say we're interested in finding the probability. So what is the probability that a randomly selected person developed lung cancer. So in this sample, what's the probability that a randomly selected person developed lung cancer? So what we're looking at here is based on the contingency table, we're actually asking for what is the probability of B. And how we can determine that from the contingency table, if we go back, we want to look at the total number of people in the category B and divide that by the total number of people in the whole sample space S. So in other words, if we're literally computing this calculation from the contingency table, we're looking at the column total for B divided by what we call the grand total, which is the bottom right corner. And that is going to give us 23 over 200, which is, if we're using a decimal approximation, that is 0.115 exactly. Okay. And we can use probabilities for the addition rule this way. Okay. So, for instance, let's have another question. So what's the probability now that a randomly selected person did not use? So probability randomly selected person did not use e-cigs or developed cancer. In other words, what we're looking for is the probability of A bar union B. So what tells us that I needed to find this? So did not use e-cigs is telling us we're interested in A bar. Or tells us union, and developed cancer is B. So we can do this using the addition rule, right? So this is probability of A bar plus probability of B minus the probability of the intersection of these two events. So probability of A bar, which is 155 over 200, plus probability of B, which we just found, which is 23 over 200, minus the probability of the intersection of those, is to look at the individual cell that's in common for both that row and column. So since we're looking at A bar B, then that's going to be the 4 over 200, which is 155 plus 23 minus 4 gives us 26. No, that's wrong. So A bar, the row total. No, I've done this correctly. Okay, so the book has a typo, and I will clarify that in a second. So 174 over 200. And that will be roughly 0.87. Alternatively, at this step, we could have done the row total for A bar plus the column total for B minus the cell for A bar intersect B. And it would give us the same thing, that whole thing in the numerator, divided by the grand total, and it should give us the exact same probability.